Hold uranium ore in bare hands and you'll absorb radiation equivalent to chest X-ray. Uncomfortable but survivable. Process that ore into fuel pellets and proximity alone could kill within hours. This dull gray rock powers 9% of global electricity, lighting 100 million American homes continuously. A single pellet the size of Gummy Bear contains energy equivalent to 1 ton of coal, 150 gallons of oil, or 17,000 cubic feet of natural gas. How does radioactive stone become civilization's most concentrated energy source? Why does fuel that could power city for years start as rock you could safely hold? Stay with us. You'll witness mining operations extracting invisible danger from ordinary-looking mountains and discover uranium's shocking paradox. The deadliest industrial material humanity handles, yet statistically the safest energy source ever deployed. Cigar Lake Mine in Saskatchewan, Canada sits 1,800 feet underground, deepest high-grade uranium mine operating. The ore body contains 18% uranium, 300 times concentration of typical deposits. The mine processes 9 million pounds of uranium annually, enough to fuel 40 nuclear reactors. Workers never touch the ore directly. Remote-controlled machinery operated from surface-level mines the deposit through jet boring. High-pressure water-cutting ore while operators watch via cameras miles away. Watch the production floor. Ore slurry pumps to surface through pipes, never exposed to air. The processing building operates under negative pressure. Air flows inward only, preventing radioactive dust escape. Radiation detectors cover every surface. Alarms sound if readings exceed 0.005 millisieverts per hour. Strict limits protecting workers from cumulative exposure. The operation resembles biological containment facility more than traditional mine. Every tool, every surface, every worker gets monitored continuously. This isn't mining, it's surgical extraction of atoms. Milling transforms ore into Yellowcake, uranium oxide concentrate appearing as actual yellow powder, hence the name. The ore gets crushed to sand consistency, then dissolved in sulfuric acid. Uranium separates from waste rock through chemical precipitation. The resulting Yellowcake contains 80% uranium, still not weapons grade, not reactor ready, but concentrated enough to require serious precautions. The tailings, waste rock after uranium extraction, remain radioactive for thousands of years. Mills create tailings ponds the size of small lakes, lined with synthetic barriers preventing groundwater contamination. These ponds will require monitoring and maintenance for millennia. The cost of this eternal stewardship gets built into electricity prices. Nobody mentions this when praising nuclear power's economics, but the industry accepts responsibility. Every pound of Yellowcake includes perpetual care fund for its waste. Conversion comes next. Yellowcake becomes uranium hexafluoride, a gas at moderate temperatures. This conversion happens at specialized facilities operating under international inspection. The hexafluoride allows isotope separation, the critical step differentiating reactor fuel from weapons material. Natural uranium contains 0.7% U-235, the fissile isotope that splits releasing energy. Reactors require 3 to 5% U-235. Weapons demand 90% plus. The enrichment process uses centrifuges, cylinders spinning at 70,000 RPM in vacuum. The slight mass difference between U-235 and U-238 causes fractional separation. Heavier U-238 concentrates at walls, lighter U-235 remains near center. Thousands of centrifuges arranged in cascades progressively increase U-235 concentration. The technology is highly classified. Enrichment capability means potential weapons capability. Every facility operates under constant surveillance by International Atomic Energy Agency inspectors. Fuel fabrication transforms enriched uranium into pellets. Ceramic cylinders half-inch diameter, half-inch tall, each containing more energy than ton of coal. The uranium hexafluoride gets converted to uranium dioxide powder, pressed into pellets under 50 tons pressure, then sintered at 3,000 degrees. The resulting ceramic achieves density 95% of theoretical maximum, hard as sapphire, chemically inert. These pellets stack inside zirconium alloy tubes, fuel rods 12 feet long, containing 300 pellets each. The zirconium cladding serves dual purpose, contains radioactive fission products while allowing neutron transmission. 200 fuel rods bundle together as fuel assembly. A typical reactor core contains 150 assemblies, 80,000 pellets total. This arrangement will generate electricity for 18 months before requiring replacement, producing 6 billion kilowatt hours, enough to power 500,000 homes continuously for a year and a half. The reactor vessel is where uranium's true nature reveals itself. Water surrounding fuel assemblies serves triple duty: moderator slowing neutrons, coolant removing heat, and radiation shield. When neutron strikes U-235 nucleus, the atom splits, releasing energy as heat plus additional neutrons. Those neutrons strike other atoms, creating chain reaction. Control rods containing boron absorb excess neutrons, regulating reaction rate. The engineering precision is absolute. Water temperature maintained within 2 degrees. Pressure stays at 2,250 psi. Neutron flux gets monitored at 50 locations simultaneously. Computers adjust control rod positions thousands of times daily, maintaining criticality. That delicate balance where each fission triggers exactly one more fission. Too few neutrons, reaction stops. Too many, it accelerates exponentially. The reactor operates at knife edge between shutdown and meltdown, held stable through automated control systems responding in milliseconds. Spent fuel emerges deadlier than when it entered. After 18 months, the pellets contain plutonium, cesium, strontium, elements that didn't exist in original fuel, created by nuclear reactions. This spent fuel is unshieldably radioactive. Standing 10 feet away delivers lethal dose in minutes. It gets stored underwater in cooling pools for minimum 5 years while short-lived isotopes decay. Then it transfers to dry cask storage, steel cylinders inside concrete shells, passively cooled by air circulation. These casks will sit at reactor sites for decades, possibly centuries, waiting for permanent repository that may never be built. Yucca Mountain in Nevada was supposed to solve this, defunded after $20 billion spent. The waste accumulates, 90,000 tons in America alone, growing by 2,000 tons annually. The industry promises solutions always 20 years away. Meanwhile, highly radioactive material sits in temporary storage, becoming increasingly permanent. Future generations inherit this stewardship obligation, payment for electricity we consumed. Uranium's energy potential was theoretical until 1938, when Otto Hahn and Fritz Strassmann achieved first artificial nuclear fission. The Manhattan Project weaponized this discovery, creating atomic bombs by 1945. The same physics powering weapons could generate electricity. President Eisenhower's Atoms for Peace program in 1953 launched civilian nuclear power. The first commercial reactor, Shippingport in Pennsylvania, began operation in 1957. By 1970s, nuclear power seemed destined to dominate. Then 3 Mile Island in 1979, Chernobyl in 1986, Fukushima in 2011. Each accident eroded public trust. Yet 440 reactors operate globally today, generating 10% of world electricity. France gets 70% power from nuclear. America operates 93 reactors, producing 20% of electricity from fuel requiring no combustion, emitting 0 carbon during operation. Carbon emissions comparison is stark. Nuclear generates 25 times less CO2 per kilowatt hour than natural gas, 75 times less than coal, considering full life cycle including mining and decommissioning. Industry prevents emission of 2 billion tons CO2 annually versus fossil fuel equivalents. Land use is minimal. Entire nuclear facility occupies less space than single wind farm, generating equivalent power. Here's the secret we promised. Uranium is simultaneously the most dangerous and safest energy source humanity employs. The paradox is real. Spent fuel remains deadly for millennia, yet nuclear power causes fewer deaths per kilowatt hour than any alternative including solar and wind. Coal kills through air pollution, gas through climate change, hydro through dam failures. Nuclear's worst disasters, Chernobyl, Fukushima, caused fewer deaths than single coal mine collapse. The psychological terror of radiation overshadows statistical reality. From Saskatchewan mines to reactor cores worldwide, the transformation completes. We've harnessed atom splitting, the fundamental force binding matter, to boil water and spin turbines. The process is absurdly elegant. Universe's most powerful reaction employed in Victorian-era steam engine technology. That light switch you flip might close circuit powered by atoms splitting 1,800 feet underground, their energy extracted through physics discovered less than a century ago. We barely understand what we're doing, yet it works. Cleanly, efficiently, terrifyingly well. Uranium doesn't just power cities, it illuminates our species' audacity, our brilliance, and our willingness to embrace danger for progress. What if I told you that every gallon of gasoline contains traces of life that existed on Earth millions of years ago? And without it, the modern world would simply grind to a halt. Every year, humanity burns energy born from prehistoric plants, plankton, and creatures that vanished long before humans even appeared. But almost no one knows how a black, dirty mixture from miles underground transforms into a clear liquid capable of powering billions of engines. Inside oil refineries, processes unfold that resemble controlled chaos. Temperatures like inside furnaces, pressures that can tear through metal, and molecules that get broken apart and reassembled. And if you stick around till the end, you'll find out which stage of gasoline production actually determines whether your car will run or not. It all starts with crude oil pumped from underground, sometimes from depths of several miles down. This oil isn't some uniform substance. It's a complex mixture of thousands of different hydrocarbons that formed over millions of years from the remains of ancient organisms. Picture this. Dinosaurs, prehistoric plants, and plankton got transformed under pressure and heat into what now powers modern civilization. Wild fact, right? When oil gets extracted, it looks different depending on the field. It can be almost black and thick as molasses, or it can be lighter and more fluid. Mixed inside are molecules of varying sizes, from tiny gases to massive heavy components. And the refinery's job is to separate this entire mixture into useful products, one of which is gasoline. The first and most crucial stage is called fractional distillation. Crude oil gets pumped into a massive vertical tower that can reach the height of a 15-story building. This tower is called a fractionating column, and it operates on a simple principle. Different substances boil at different temperatures. First, the oil is heated to around 750 degrees Fahrenheit in a special furnace. At this temperature, most components of the crude oil turn into vapor. This hot vapor mixture enters the bottom of the fractionating column. Inside the tower, dozens of horizontal plates called trays sit at different heights. And this is where the real magic of separation begins. When hot vapor rises up the column, it gradually cools down. At each level, the temperature is slightly lower than the one below it. Heavy molecules with high boiling points condense first, at the bottom of the column, where it's still hot. Lighter molecules rise higher until they reach a level with their condensation temperature. There, they turn back into liquid and collect on the corresponding trays. The lightest gases, like propane and butane, pass through the entire tower and exit at the top at temperatures around 90 degrees. A bit lower, at temperatures from 150 to 400 degrees, the gasoline fraction collects. These are the molecules we're interested in. Even lower by temperature, you get kerosene and diesel fuel, and at the very bottom remains heavy fuel for ships and raw material for asphalt. But here's the kicker. If you just separate crude oil into fractions, you don't get that much gasoline, right? Maybe 15 or 20% of the total volume. And the demand for gasoline is massive, way bigger than what naturally exists in crude. So refiners came up with a clever way to make more gasoline from what they've got. A process called cracking. Cracking is breaking big heavy molecules into smaller ones that work for gasoline. There are a few ways to do this. Thermal cracking simply heats heavy oil to extreme temperatures around 900 degrees Fahrenheit under high pressure. Under those conditions, long chains of carbon atoms literally snap into shorter pieces. An even more effective method is catalytic cracking. Here they use special catalyst substances, usually aluminosilicates, that speed up chemical reactions without heating to such insane temperatures. Heavy oil gets mixed with hot catalyst powder at temperatures around 1800 degrees Fahrenheit, and the molecules split way faster and more efficiently. After the reaction, the catalyst gets regenerated and used again and again. There's also hydrocracking, where on top of high temperature and a catalyst, they add hydrogen under pressure, up to a ton or even 1,500 pounds per square inch. Hydrogen helps clean up the molecules, removing sulfur and nitrogen that can be harmful. This process produces the cleanest, highest quality gasoline. But even after all these transformations, gasoline still isn't ready to hit your tank. You need to improve its properties through processes called reforming and alkylation. Reforming changes the structure of gasoline molecules, increasing its octane rating, a measure of how resistant the fuel is to knocking in the engine. Low-octane gasoline can ignite prematurely in the engine cylinders, causing a knocking sound and potentially damaging the motor. During reforming, gasoline molecules pass through a series of reactors with platinum catalysts at temperatures around 900 degrees. There, straight chains of atoms rearrange into branch structures and ring molecules, which have higher octane ratings. Lead used to be added to boost octane, but it turned out to be toxic and polluted the environment, so it was phased out back in the 1990s. Alkylation is the process of combining small molecules into bigger ones, but perfectly sized for gasoline. It takes light gases created during cracking and joins them together using strong acids to make molecules of just the right size with high octane numbers. It's an expensive process, but it produces premium gasoline components. After all these transformations, different gasoline streams get blended in precise proportions to create the final product with the desired characteristics. A bunch of additives get thrown into the mix too, substances that improve various properties. Detergents clean engine deposits. Antioxidants prevent gasoline from degrading during storage. Corrosion inhibitors protect the fuel system from rust. Dyes get added so different types of gasoline can be distinguished visually. In many countries, ethanol is added to gasoline by law, an alcohol made from corn or sugarcane. Usually it's 10% by volume, though sometimes more. Ethanol boosts the octane rating and is considered more environmentally friendly because it comes from renewable sources, though there's debate about whether it's actually that beneficial for the environment, considering all the energy spent growing the raw materials. Interestingly, from 1 barrel of crude oil, 42 gallons, you get about 5 gallons of gasoline plus diesel, kerosene, lubricants, and other products. Nothing goes to waste. Even the gases produced in the process are burned to heat the refinery itself, or converted into other useful substances. A modern oil refinery is a city of pipes, towers, reactors, and storage tanks that can span several square miles. The entire complex is run by computers that monitor thousands of parameters simultaneously: temperature, pressure, flow rates, product composition. A mistake in the settings can cost millions of dollars, or even lead to a catastrophic accident. Environmental standards are getting tougher, so refineries are constantly being upgraded, installing new equipment to clean emissions, cutting energy consumption. Gasoline production has become significantly cleaner than it was 30 or even 40 years ago, though it still remains energy intensive and has an impact on the environment. This entire complex system exists, so you can just pull up to a gas station, stick the nozzle in your tank, and fill up in a couple of minutes. Behind those few minutes stand geologists searching for oil, engineers designing wells and refineries, chemists developing catalysts and additives, technicians keeping equipment running, drivers delivering fuel, a global industry working around the clock to keep the world moving. And while there's a lot of talk right now about electric vehicles and renewable energy, gasoline will remain the primary fuel for billions of cars around the world for a long time to come. It's the product of a century of engineering thought, chemical research, and technological innovation, transforming ancient organic matter into the energy of today. Watch liquid steel pour from a ladle, glowing white at 3,000 degrees, bright enough to burn your retinas instantly. 20 tons cascading like luminous waterfall into molds, each splash throwing sparks 50 feet. This isn't new steel from ore, it's recycled. Yesterday's junked cars, demolished buildings, scrapped appliances melted and reborn. America recycles 80 million tons of steel annually, more than all other materials combined. That rebar in your building's foundation? Average age: 73 years through 4 previous lives. How does rusted scrap transform into structural steel stronger than original? Why does recycled steel outperform virgin steel in crucial applications? Stay with us. You'll witness industrial-scale alchemy turning garbage into skyscrapers and discover steel's shocking secret. It's infinitely recyclable without quality loss, forever. Nucor Steel's Berkeley facility in South Carolina processes 3 million tons annually, enough steel to build 15 Golden Gate bridges yearly. The scrapyard stretches half a mile, mountains of metal sorted by type. Shredded cars pile 6 stories high. Railroad rails stack like pickup sticks. Crushed appliances form metal glaciers. Giant cranes with electromagnets strong enough to lift entire automobiles move continuously, sorting, stacking, organizing chaos. Watch the shredder operation. A hammer mill the size of 2-story house contains rotating drum with 50 hammers, each weighing 300 pounds. Cars feed in whole, no disassembly required. In 8 seconds, automobile becomes fist-sized chunks. The noise defies description. Continuous thunder as metal destroys metal. The shredder processes 100 cars hourly, 6,000 monthly. Every junked vehicle in America eventually passes through facilities like this. Nothing wastes. Even copper wiring gets separated and recycled independently. The electric arc furnace, EAF, is where steel is reborn. This vessel, 40 feet diameter and 30 feet deep, operates through electrical violence. 3 graphite electrodes, each 2 feet thick and 15 feet long, descend from the roof. When power flows, 90 megawatts, enough electricity for 70,000 homes, arcs jump between electrodes and scrap, generating temperatures exceeding 5,000 degrees. The initial charge contains 200 tons of scrap steel loaded via overhead buckets. Operators lower electrodes carefully. Too fast, they shatter. Too slow, productivity suffers. The arc strikes with deafening crack, visible through protective glass as blinding white plasma. Metal begins melting immediately. The sound evolves from cracking to roaring as molten pool forms. Watching through infrared cameras reveals the chaos: solid metal liquefying, impurities rising as slag. The melt cycle takes 45 minutes start to finish. Chemistry happens through violence and precision simultaneously. Oxygen lances inject pure oxygen into molten steel at supersonic speeds. The oxygen burns impurities, carbon, sulfur, phosphorus, creating slag that floats atop the denser steel. Temperature reaches 5,800 degrees at plasma core, hot enough to vaporize iron itself. Cooling water circulates through furnace walls at 5,000 gallons per minute, preventing meltdown. Alloying additions fine-tune steel composition. Computer-controlled systems add precise amounts of manganese, chromium, nickel, elements determining final properties. High-strength rebar requires different chemistry than structural beams. The metallurgist's console displays real-time analysis via spectrometer. Laser vaporizes steel sample. Computer analyzes emitted light, identifying every element present to parts per million accuracy. Adjustments happen in real time. Chemistry perfected before tapping begins. Tapping releases the dragon. The furnace tilts hydraulically, massive vessel rotating on trunnions. Molten steel pours through tap hole into waiting ladle. Refractory-lined bucket containing 40 tons of liquid metal. The pour takes 6 minutes. Continuous stream of glowing steel creating updrafts so powerful, they lift dust and debris into the air. The temperature, 3,050 degrees, radiates heat felt 200 feet away. The ladle, mounted on railcar, travels to continuous caster. This machine revolutionized steelmaking, replacing individual mold casting with endless process. Molten steel flows from ladle into tundish, then into water-cooled copper molds oscillating up and down. As steel contacts mold, outer shell solidifies while interior remains molten. The strand, continuous ribbon of steel 8 inches square, emerges from bottom at controlled speed, bent gradually from vertical to horizontal through roller system. The hot rolling mill is where shape is born. The continuous cast billet, still glowing red at 2000 degrees, enters the roughing mill. Giant rollers, each weighing 30 tons, squeeze the steel, reducing thickness while increasing length. The transformation is violent. 8-inch square becomes flat bar 6 feet wide and quarter-inch thick in 7 passes through successive roller stands. Watch the mill operation. The steel screams through at 40 miles per hour, extending like taffy as rollers compress it. Water jets cool rollers constantly. Without cooling, the steel would weld itself to roller surfaces. Scale. Iron oxide forming on surface gets blasted away by high-pressure water, creating permanent rainbow mist in the mill. The noise is beyond hearing protection. Low-frequency vibration felt in bones. One operator describes it. Steel doesn't want to be flat. We convince it otherwise through controlled violence. Cooling determines final properties through metallurgical magic. After final rolling pass, steel enters cooling bed, where water jets precisely control cooling rate. Fast cooling creates hard, brittle steel. Slow cooling produces soft, ductile steel. Controlled cooling, varying rates across thickness, creates exactly desired microstructure. Computer systems adjust water flow based on steel grade, thickness, ambient temperature. The coiler winds finished steel into massive coils, 40 inches wide, 1 mile long, weighing 25 tons. These coils ship to manufacturers producing everything from automobiles to appliances. Some steel goes to galvanizing lines where molten zinc coating prevents rust. Other steel gets further processed, cold rolled for precision applications, annealed for formability. But the core material, recycled steel, remains unchanged, ready for another century of service. Steel recycling accelerated during World War II when scrap drives collected every available piece of metal for weapons production. Post-war, technological advances made recycling economically viable. The electric arc furnace, developed in 1960s, eliminated need for iron ore. Recycling became primary production method. By 1980s, mini mills using EAF technology revolutionized the industry, undercutting integrated mills using blast furnaces. Today, America produces 70% of steel from recycled scrap. Traditional integrated mills using iron ore and blast furnaces still exist but increasingly rely on scrap supplementation. The transition reflects economic and environmental reality. Recycling uses 60% less energy than primary production. A single steel mill prevents mining hundreds of thousands of tons of iron ore annually. The industry transformed from extraction to circulation, steel cycling endlessly through economy. Carbon emissions dropped 65% using recycled steel versus virgin production. Industry saves $58 billion annually avoiding ore mining and processing. Each recycled ton prevents 4 tons of raw material extraction, ore, coal, limestone combined. Here's the secret we promised. Steel is infinitely recyclable without degradation. Unlike plastic degrading with each recycle, steel maintains properties indefinitely. That nail holding your wall could have been Roman sword, railroad spike, Model T chassis, World War II tank, 1960s Cadillac, demolished skyscraper, and now construction steel. Same iron atom serving humanity for millennia. The crystal structure reforms perfectly during melting, erasing all history. Impurities burn away in the furnace, chemistry optimized through modern metallurgy. From junkyard to job site, the transformation completes. We've created closed-loop system where waste becomes resource, garbage becomes infrastructure. That bridge you drove across, those rails carrying freight, the frame supporting your office, all contain steel recycled dozens of times. The metal never tires, never weakens, never remembers its past. We've mastered material that improves through use, strengthened by human engineering beyond nature's intention. Steel isn't consumed. It circulates, eternally useful, permanently valuable, waiting only to be reshaped for next purpose. Civilization built on metal that refuses to die.
Stand beside the world's largest diesel engine. It towers 44 feet tall, higher than a 4-story building, stretches 89 feet long, longer than a semi-truck with trailer. 14 cylinders, each wider than oil drum, fire in sequence, producing 109,000 horsepower. That's the power of 1,600 cars concentrated in one single machine. This engine burns 250 tons of fuel daily, moving 20,000 containers across oceans at 23 knots. How does metal combusting heavy fuel oil generate force pushing 90,000-ton ships through water? Why build engines this enormous when smaller multiples could work? Stay with us. You'll discover the brutal elegance of two-stroke combustion at massive scale, and the shocking secret of why these engines burn fuel refineries consider waste. The cheapest, dirtiest.
Our journey begins at Hyundai Heavy Industries in Ulsan, South Korea, the shipyard building these mechanical titans. The engine manufacturing hall spans 30 acres under single roof. Overhead cranes rated at 600 tons glide on rails, positioning cylinder blocks weighing as much as locomotives. Workers look like ants beside components. Watch the cylinder casting. Molten iron pours into sand molds, creating a single cylinder liner. Hollow tubes where pistons travel. Each liner stands 12 feet tall, walls 4 inches thick. The iron must cool for 72 hours. Rush it, thermal stresses create microscopic cracks that propagate under operation, causing catastrophic failure. We make engines that run 30 years continuously, explains Chief Engineer. No second chances if casting fails.
The crankshaft arrives on specialized trucks, a single forged steel shaft weighing 300 tons, machined to tolerances measured in thousands of inches across 70-foot length. Installing it requires choreographed precision. Hydraulic jacks lift the shaft while technicians align bearing surfaces. One misalignment of ½ inch causes bearing failure within weeks of operation. Picture the assembly floor. 14 cylinder liners bolt to engine block, itself a 40-foot steel casting, forming engine skeleton. Each connection uses bolts diameter of baseball bats, torqued to specifications requiring pneumatic impact wrenches lasting 5 minutes per bolt. Assembly takes 6 months, 12-hour shifts, teams of 50 engineers and technicians. One finished engine represents 200,000 man-hours, equivalent of one person working full-time for 96 years straight.
The pistons dwarf automobile engines. Each piston assembly, piston, rings, and connecting rod weighs 6 tons. That's heavier than full-sized pickup truck. The piston crown, exposed to combustion, endures temperatures exceeding 1,800 degrees and pressures reaching 2,000 psi. Material science pushes limits here. Watch piston installation. Cranes lower assemblies through cylinder tops. Workers guide them onto connecting rod bearings with millimeter precision. The piston rings, spring steel bands sealing combustion pressure, get installed by hand. Each ring expands under tension, slip during installation, and the ring snaps, injuring workers and destroying components worth $50,000. Veterans develop feel for tension, installing rings quickly yet carefully. 20 years I've installed 3,000 pistons, says one assembler. Still respect every one.
Now grasp two-stroke operation. Elegantly simple, yet counterintuitive. Unlike car engines firing every other rotation, marine diesels fire every rotation. As piston descends, it uncovers ports in cylinder wall. Compressed air rushes in, pushing exhaust out simultaneously. The piston rises, compressing fresh air. Near top, injectors spray heavy fuel oil. Compression heat, not spark plugs, ignites fuel. Explosion drives piston down. The cycle repeats. This two-stroke design eliminates valves entirely. No camshafts, no timing chains. Fewer parts mean greater reliability. But it demands supercharging. Turbocharges forcing air into cylinders at 22 psi. Without pressurization, the engine wouldn't breathe.
Turbochargers the size of sedans spin at 20,000 RPM, driven by exhaust gas. They glow red-hot during operation, requiring water cooling systems circulating thousands of gallons hourly.
Fuel injection happens at extreme precision. Each cylinder consumes 16 gallons per combustion cycle, enough to fill your car's tank every few seconds. Injectors spray fuel as fine mist under 6,000 psi pressure. The atomization must be perfect. Droplets too large won't burn completely, wasting fuel. Too fine, combustion becomes explosive rather than controlled, damaging engine. The fuel itself surprises people. These engines burn heavy fuel oil, basically petroleum refinery leftovers after extracting gasoline, diesel, and jet fuel. It's thick as molasses at room temperature, must be heated to 240 degrees before flowing. Contains sulfur, metals, and contaminants that would destroy car engines instantly. But marine diesels tolerate it because economics dictate everything. Heavy fuel costs 40% less than automotive diesel. At 250 tons daily, that price difference means millions saved annually per ship.
Engine control happens from bridge via computer systems monitoring 600 parameters simultaneously. Engineers track cylinder temperatures, bearing pressures, fuel consumption, turbocharger speeds. The engine room, 3 decks tall, deafeningly loud despite ear protection, houses the mechanical orchestra. Walk the engine room during operation. Heat radiates from every surface. Metal creaks and groans as thermal expansion moves components fractions of inches. Across a 70-foot engine, that's feet of total movement. The crankshaft, visible through inspection ports, spins at 102 RPM. Seems slow until you realize this massive shaft accelerates tons of metal from 0 to maximum speed every single rotation. The forces involved bend physics. One chief engineer describes it, "This isn't machinery, it's controlled violence. We're detonating tons of fuel hourly inside metal box, converting explosions into rotation." Maintenance happens at sea on schedules measured in years. Every 8,000 hours, roughly 1 year of operation, crews perform major service. They drain lubricating oil, 60,000 gallons per engine, replacing filters the size of trash cans. Inspect cylinder liners for wear using ultrasonic equipment. Pull pistons for ring replacement. The most dramatic maintenance involves crankshaft inspection. Engineers use magnetic particle testing, apply magnetic field, spray iron particles, look for cracks where particles accumulate. Finding cracks in 300-ton crankshaft spinning at 100 RPM means potential catastrophic failure. The process takes 4 days of continuous work while ship sits idle, losing $200,000 daily in lost revenue. But catching cracks before failure saves the engine worth $15 million. No shortcuts exist. We maintain like lives depend on it, states Chief Engineer, because they do. Rudolf Diesel invented compression ignition engines in 1897, demonstrating fuel efficiency double that of gasoline engines. His original design ran on peanut oil. Diesel envisioned farmers powering equipment from crop byproducts. The petroleum industry hijacked his invention, optimizing for their cheapest product, heavy fuel oil. Marine applications began in 1920s. By 50s, diesel surpassed steam turbines. The two-stroke design, perfected by Sulzer and Wärtsilä through 70s and 80s, became dominant. Today's largest, the Wärtsilä-Sulzer RTA96C, produces power exceeding small city power plant. Just 14 cylinders generating 109,000 horsepower. 23,000 containers moved by single engine. 98% of ocean cargo moves via diesel-powered ships. These engines literally keep global economy flowing.
Carbon emissions seem paradoxical.
These engines burn dirtiest fuel, yet achieve 48% thermal efficiency, converting nearly half consumed energy into motion. Modern cars manage 25%. The efficiency comes from slow operation and massive scale, allowing effective heat recovery through turbochargers and economizers. Here's the secret we promised. Marine diesels burn fuel refineries would otherwise struggle disposing. That heavy fuel oil, thick, contaminated, full of sulfur, represents petroleum industry's bottom-of-barrel waste. Refineries initially paid ships to remove it. Marine engines transformed waste into commodity. Today, heavy fuel powers 90% of ocean shipping. Those engines burning waste move 60 billion tons of cargo annually, generating 3% of global carbon emissions, while handling 90% of international trade. From refinery waste to global commerce, the cycle completes. We've built machines so large they boggle comprehension, burning fuel so crude it seems impossible, moving cargo quantities that dwarf imagination. That container ship Horizon, powered by controlled explosions in cylinders taller than you, spinning crankshafts heavier than your house, burning fuel thicker than syrup. Engineering at scale where normal physics seems inadequate, yet it works reliably, efficiently, endlessly. These aren't just engines, they're the beating hearts of globalization itself.
Inside a steel mill, molten iron glows white at 3,000 degrees. Workers stand 50 feet away. The radiant heat still blisters exposed skin. But look closer at what contains this liquid fire. Gray bricks line the furnace walls, glowing dull orange, yet holding firm. These aren't ordinary bricks. Touch regular clay brick to molten metal and watch it explode into steam and fragments. So what material survives temperatures hotter than volcanic lava? What invisible shield protects every furnace melting metal, making glass, or firing ceramics worldwide? Stay with us. You're about to discover why engineers kill clay to make it stronger, and the counterintuitive secret of double firing that transforms fragile earth into industrial armor, surviving conditions that vaporize steel.
Our story begins in Missouri clay. Deposits formed 60 million years ago when ancient seas deposited aluminum-rich sediments. Excavators rip into hillsides, extracting clay containing over 40% alumina, the magic ingredient. Regular pottery clay melts around 2,000 degrees. High alumina clay? It laughs at 3,000. Watch the extraction crew. They're not just digging dirt, they're harvesting geology's accident. This specific clay formed under precise conditions. Volcanic ash settling through prehistoric oceans, compressed over epochs. The foreman walks the pit daily, examining color and texture. Too much iron content, the clay turns red and weakens. Perfect batches shimmer gray-white, almost ghostly. Every ton supports industries most people never see, but everyone depends on.
The clay arrives at processing facilities caked with impurities. Massive crushers reduce house-sized boulders to gravel. Water floods the mixture, creating liquid slurry pumped through magnetic separators. Powerful magnets extract iron particles. Even microscopic contamination causes problems later when heat turns iron into weak spots. Picture the filtration building. Workers monitor screens showing particle sizes measured in microns. The slurry flows through increasingly fine meshes, removing everything except pure clay molecules. The process mirrors diamond cutting, patient, meticulous, unforgiving. One foreman's been doing this 30 years. Clay's honest, he says. Screw up purification, the furnace tells you months later when bricks fail. By then, you've shut down a steel mill.
Here's where it gets strange. Before making bricks, they destroy the clay. Giant kilns, tunnel ovens stretching 300 feet, fire raw clay at 2,400 degrees. The material transforms. Water molecules trapped in crystal structure evaporate. Crystals fuse together. The clay dies, becoming chamote, fired aggregate resembling brown gravel. Watch workers dump glowing chamote onto cooling floors. Steam erupts as residual moisture hits air. The material has lost its plasticity forever. You can't reshape it. You can't mold it. Ancient potters would call this ruined clay. Modern engineers call it the secret ingredient. This dead material becomes the skeleton that prevents shrinkage when the final brick gets fired. It's already survived hell once, it won't flinch the second time.
Now the resurrection begins. Crushers pulverize chamotte into particles ranging from sand size to powder. Meanwhile, fresh raw clay gets mixed with water, creating a binding paste. The ratio matters obsessively. 70% dead chamotte, 30% living clay. Too much chamotte, the brick crumbles. Too little, it shrinks catastrophically during final firing. Imagine construction workers mixing concrete, but every batch costs thousands, and failure means industrial catastrophe. The mixing drums rotate for 40 minutes. Technicians pull samples constantly, checking consistency. The mixture emerges as damp, grainy paste. Looks like chunky peanut butter, but feels like dense sand. This strange hybrid contains both the dead and the living, the fired and the raw, the stable and the flexible.
Hydraulic presses generate forces exceeding 2,000 tons, compressing the clay chamotte mixture into brick shapes. The pressure is critical. It determines density, which determines strength. Watch the press operator. He's worked this machine 18 years. His hands hover over emergency stops, eyes tracking pressure gauges. The bricks emerge slightly damp, surprisingly fragile. You could break one with a hammer. Workers stack them on kiln cars, steel platforms holding thousands of bricks. The cars roll into drying chambers where warm air removes moisture over 72 hours. Dry too fast, surface cracks. Too slow, production bottlenecks. The drying supervisor walks the chambers constantly, adjusting airflow by feel and decades of experience.
The final firing begins. Kiln cars enter tunnel kilns heated to 2,600 degrees. The journey takes 48 hours, crawling through zones of increasing temperature. In the first zone, remaining moisture evaporates. Second zone, raw clay begins sintering, particles fusing at edges. The critical third zone pushes temperatures beyond anything the bricks will face in service. You can't see inside operating kilns. The heat would blind you instantly. But infrared cameras reveal the transformation. The bricks glow yellow, then white. At peak temperature, individual clay particles fuse into dense ceramic matrix. The chamotte, already fired once, provides dimensional stability, preventing the shrinkage that would crack ordinary clay. When bricks finally exit, they've transformed into material that will outlast the furnaces they protect. Quality control seems simple. Drop the brick. It should ring like a bell. Clear, sustained tone indicates proper firing and density. Dull thuds mean hidden cracks or insufficient firing. Experienced inspectors can diagnose problems from sound alone. "That's a Saturday brick," one inspector says, tapping a dull specimen. "Someone rushed the firing before weekend. Rejected." But sound testing is just the start. Samples get crushed in hydraulic presses, measuring compressive strength exceeding 10,000 psi. Others get thermal shocked, heated to 2,000 degrees, then water quenched. Survivors prove they'll handle the brutal thermal cycling of industrial furnaces. Failure rate must stay below 0.5%. Even one weak brick can collapse a furnace wall, causing million-dollar shutdowns.
Refractory technology emerged from ancient pottery kilns. Early Chinese potters discovered high alumina clay fired harder than anything else. By 1300 AD, Chinese furnaces using primitive refractories reached temperatures melting iron, a feat Europeans wouldn't match for 4 centuries. The Industrial Revolution demanded better. In 1879, Sidney Gilchrist Thomas invented basic refractory lining, enabling the Bessemer process to use phosphorus-rich iron ore. Suddenly, Britain's massive ore deposits became viable. The discovery shifted global power. Whoever controlled refractory technology controlled steel production. Today, specialized refractories enable everything from semiconductor manufacturing to rocket engines. The global industry moves 50 million tons annually. Invisible infrastructure supporting visible civilization.
Carbon emissions dropped 41% using modern refractories versus 1950s technology. Better insulation means less fuel heating furnaces. Industry saves $78 billion annually through extended furnace life. Modern refractories last 5 years versus 6 months for old materials, slashing replacement costs. Here's the secret we promised. Refractory bricks work because they're already dead. That double firing process, burning the clay into chamont, then mixing it with fresh clay and firing again, creates material that's experienced worse than anything it'll face. The chamont has no shrinkage left to give. The fresh clay binds it together, then dyes itself during final firing, becoming equally stable. From ancient clay to modern armor, the cycle completes. We've learned that sometimes strength requires destruction first. Kill the material, resurrect it, kill it again. Only then does it become immortal, standing guard in furnaces that never sleep, protecting the industrial processes, keeping civilization running. That humble gray brick isn't just holding back heat, it's holding back chaos.
Without nickel, Tesla's electric vehicles wouldn't exist. Every year, over 3 million tons of this silvery metal get extracted from Earth's crust, 70% destined for stainless steel, 30% powering the battery revolution transforming transportation. Picture this. Inside every electric car battery, nickel accounts for up to 80% of cathode weight, storing the electrical energy making 500-mile ranges possible. How does rock buried 2 miles underground become the metal enabling carbon-free futures? How do ancient asteroid impacts create deposits worth billions? Stick around till the end. You'll discover why this metal, discovered in 1751, became overnight the most critical resource for climate solutions, and the shocking environmental price we pay for every kilowatt-hour stored. The story begins in Sudbury, Canada, ground zero for one of Earth's largest meteorite impacts. 2 billion years ago, a 6-mile-wide asteroid slammed into primordial crust with force equaling 6 billion Hiroshima bombs. That cataclysmic collision melted rock 60 miles deep, concentrating nickel-rich magma into deposits mining companies extract today. Standing at crater's edge feels like visiting Earth's wound that never healed. Modern mining descends through vertical shafts, plunging 7,000 feet, deeper than 6 Empire State Buildings stacked vertically. Massive cage elevators, traveling at speeds exceeding 30 miles per hour, drop miners into darkness in under 4 minutes. That's falling through bedrock older than complex life itself. Underground, temperatures reach 120 degrees Fahrenheit from Earth's geothermal heat, requiring industrial air conditioning, pumping cold air through 40-mile tunnel networks. Next comes extraction, where explosive specialists drill blast holes following nickel-bearing veins. Charges containing ammonium nitrate, industrial explosive used in quantities measured by tons, fracture solid rock with controlled violence. The deafening thunder from underground blasts shakes surface buildings miles away, rattling windows in synchronized waves every afternoon at precisely 4 o'clock shift change. Giant load haul dump machines, nicknamed LHDs, and standing tall as double-decker buses, scoop 50 tons per bucket. Picture mechanical mastodons navigating tunnels barely wider than their frames. Operating in perpetual darkness illuminated only by headlamps, Drivers maneuver 60-ton machines through labyrinths where wrong turns mean hours backtracking. Every shift, these machines transport 15,000 tons of ore, weight equivalent to 75 blue whales, through underground highways to crushing stations. Surface processing begins where jaw crushers, standing 4 stories tall with opening widths matching garage doors, pulverize boulders into gravel-sized chunks. With bone-rattling vibrations felt through steel-toed boots, hydraulic jaws generate crushing forces exceeding 15,000 pounds per square inch. Operators monitor crack propagation. Rocks splitting wrong create jams requiring dangerous manual intervention with jackhammers. Conveyor systems stretching 8 miles, longer than Central Park, transport crushed ore to grinding mills. Inside rotating drums 30 feet in diameter, 25-ton steel rods tumble with ore, creating grinding cacophony resembling continuous thunder. Processing 12,000 tons hourly, that's loading freight trains non-stop. This powder, finer than beach sand, flows to flotation cells where chemicals separate nickel sulfides from waste rock using bubble physics. Nickel concentrate emerges containing 20% metal, ready for the real challenge: purification. Next comes roasting, a pyrometallurgical inferno where concentrate gets heated in massive kilns to 1,400 degrees Fahrenheit. At these temperatures, sulfur burns away as sulfur dioxide, leaving behind nickel oxide mixed with iron. Picture industrial-scale barbecuing where the meat is rock and smoke contains compounds requiring scrubbing before atmospheric release. The roasted material, now crumbly and porous like volcanic pumice, moves to smelting furnaces, where temperatures climb to 2,600 degrees Fahrenheit. Electric arc furnaces, consuming power equivalent to small cities, enough electricity to run 12,000 homes, melt oxide into liquid matte. This molten mixture, containing 60% nickel and 40% other metals, glows white-hot like captured starlight. Every 2 hours, furnaces tap this liquid fire into ladles holding 200 tons. The purification process intensifies with converting, where oxygen blasted through molten matte at supersonic speeds burns away remaining sulfur and iron. Massive Peirce-Smith converters, rotating horizontal cylinders 40 feet long, operate like blast furnaces lying sideways. Inside these rotating drums, chemical warfare occurs. Oxygen attacking sulfur bonds, creating temperatures hot enough to vaporize copper. This step is critical because timing determines purity. Blow too long, nickel oxidizes wastefully. Too short, impurities contaminate final product. Operators monitor color changes in flames shooting from converter mouths. Blue flames mean sulfur burning, yellow indicates iron removal, clear white signals nickel ready. That visual chemistry, unchanged for centuries, guides decisions affecting millions in product value. After converting, nickel matte achieves 78% purity, but battery manufacturers demand 99.9%. After converting, the real magic begins: electro-refining. Here, physics and chemistry converge in massive electrode halls housing thousands of cells. Impure nickel anodes, cast into plates weighing 300 pounds each, suspend in electrolyte baths containing nickel sulfate and sulfuric acid. Electric current flowing through these baths, think industrial-scale electroplating, dissolves nickel atoms from anodes, transporting them through liquid to deposit on pure nickel starter cathodes. Picture this: over 10 days, nickel migrates atom by atom across 6-inch gaps. Impurities like cobalt, copper, iron stay behind, falling as sludge to cell bottoms. This sludge, later processed separately, contains precious metals including platinum, gold, palladium, making waste worth more than many ores. Temperature control matters critically. Too hot, dendrites form, metal crystals bridging electrodes causing shorts. Too cold, deposition slows uneconomically. Electro-refining requires surgical precision in industrial setting. Computer systems monitor voltage, amperage, temperature across 15,000 individual cells simultaneously. Operators adjust current by milliamps. Modern refineries achieve nickel purity of 99.99%, only one impurity atom per 10,000. That's purity rivaling semiconductor-grade silicon. After 10 days, workers crane lift finished cathodes, now coated with 400-pound nickel deposits from baths. Mechanical strippers peel nickel from starter sheets like removing wallpaper. These pure nickel sheets, called cathodes, get melted into pellets for battery manufacturers, or alloyed with chromium and iron for stainless steel. The energy intensity staggers. Producing 1 ton of battery-grade nickel consumes 50 megawatt-hours, enough electricity to power average American homes for 60 days. This industry transformed radically in 15 years. Back in 2010, nickel prices averaged $7 per pound, used primarily for stainless steel. Battery applications consumed less than 5% of global production. That all changed when Elon Musk's Master Plan 2 announced Tesla's battery gigafactories in 2016. The breakthrough came when battery chemistry shifted from cobalt-heavy NCAs to nickel-rich NCMs, nickel-cobalt-manganese cathodes containing 80% nickel. Suddenly, every electric vehicle needed 110 pounds of nickel. Global demand exploded. Prices spiked to $9 per pound by 2022. Indonesia, containing 21% of world's reserves, transformed from minor player to dominant producer. Today, battery applications consume 43% of new nickel production. By 2035, International Energy Agency projects batteries will consume 75%, driven by 200 million electric vehicles requiring 23 million tons cumulatively. Carbon emissions drop by 18% when recycling nickel versus mining virgin ore, equivalent to removing 3 million cars annually. Industry saves over $22 billion yearly through recycling. Processing costs drop 31% because smelting scrap requires half the energy of complete ore processing. So here's the secret promised. Nickel is humanity's transition metal, literally bridging fossil fuel era to electric future. But here's the dark truth. Extracting nickel for just one EV battery produces 8 tons of CO2 emissions. That electric car carries invisible environmental debt, requiring 35,000 miles of driving before breaking even with efficient gasoline vehicles. The green revolution isn't free. It's an energy trade-off where extraction today enables emission reductions tomorrow. From asteroid impacts to electric highways, cycle completes. We're mining ancient cosmic collisions to power climate solutions. Nickel doesn't solve pollution, it relocates it, concentrates it, transforms it into manageable problem. That's not failure, that's engineering reality. Every solution creates new challenges. The question isn't whether mining nickel harms Earth, it does. The question is whether preventing catastrophic climate change justifies temporary scars.